All right, so here we go with the second part of Chapter 5, Data and Process Modeling. I give you a little teaser in part 1 in regards to a data dictionary. So as we create a data dictionary, if we do it right, every single element of data is going to be described in that data dictionary. So the metadata that describes the data that we're going to store most likely in a database. Okay, so this information, like I said, not only used when we program an IT solution or do a project, but also tends to be used a ton after the fact. This is where report writers go to figure out, okay, I need to pull that, the customer order number, for example. Well, where the heck is that stored? And what kind of number is it? Is it a varchar? Is it an integer, etc.? Those kind of things. So that we can write reports effectively, we'll go out and figure out what table it's in because databases are huge. So we want to know where to start looking. We don't want to have to go through 50 or 100 tables to figure out where that element of data that we need to report on is. So keep that in mind. So a data dictionary or data repository, central storehouse of information about the system's data. This is the documentation, folks. Okay, so we collect, we document, we organize specific facts about the system. Now the great thing is, we can literally create one of these in Excel. I've done that before for some basic databases. Create this, and that way I can sort it by, all the different attributes of the metadata that describes the data that I'm going to store in the database. It also defines and describes all the data elements and meaningful combinations of data elements. So, where are we storing it? What's being stored with it? So a data element, also called a data item or field. So think about a database. What's a field, right? Smallest piece of data that has meaning. So elements are combined into records. So an example would be a customer record, and in a customer record, right, we would have data items or fields that describe that customer. CUST underscore F name, customer first name, customer last name, customer date of birth. You get the idea. And normalizing it, we wouldn't just have customer address, we'd have customer street number and then customer street name. That way we could sort by the street name, without having an interference from the number or the house number of the address. So good example there. A record is a meaningful combination of related data elements that is included in the data store. So if you've taken a database class, you understand what we're talking about here. So we can use use case tools for documentation. More complex the system, the more difficult it is, to maintain full and accurate documentation. Um, I've seen these things where, why do we call it a dictionary? Some of these things back in the day were as thick as a dictionary, and they were then, printed out so that a database administrator, a report writer could search. So back then, before, the whole electronic format and searching, today we might create a little database that is the data dictionary for a database, for example, so we can search and report on it. So a case repository ensures data consistency. And if you want more information about this, go into the Systems Analysis Toolkit at the end of the textbook, okay? Or turn to Part B of the 4-part toolkit, that follows Chapter 7. Part B will give you more information on the case tools used for a data dictionary. Got a couple videos in there. Make sure you watch those. Yes, they're dated in our chapter folder. Yes, they're dated, but they'll make more sense when it's described to you. So documenting the data elements, it must document every data element in the data dictionary. Well, that makes perfect sense. If we're going to store it, we need to know who, what, where, when, how, and why we're storing those data elements. The objective, of course, is the same, clear and comprehensive information about the data. So all of our documentation needs to be up to date, it needs to be clear, and it needs to be concise. So some of you, shorten things up, a label, social security number, that makes sense here, right? So here's a data dictionary entry. Okay, so online or manual documentation, you can pause and read through this. The system that it's for is the payroll system. The label for this data element, social security number. Now we wouldn't just put SSN because That might mean something to someone else as the label, but notice the alias, because most people know Social Security number as SSN, we can use an alias for that. Type and length, so 9, N, and then default value. We wouldn't have a default value, okay, because there isn't one to be had for this element of data, okay. The source, its security, we would go further involved with security, another, are we going to encrypt this data element, and if so, what table is it going in, what encryption method are we using, etc. So you get the idea. So you can go out and Google and find great examples of data dictionary entries. Okay, so documenting the elements of the data. So data element name and label. Okay, so the name, of course, is going to be a full name. The label, okay, is going to be a lot of times what we call that element in the database. Okay, so I might, reduce this down to SOC underscore SEC underscore NUM, but still something that most people would know. And if they don't know, they'll come look at the description. This is a Social Security number, standard issued by, the United States as a unique identifier, blah, blah, blah. Don't make it too verbose, but make sure there's enough information. Now, something as clear as Social Security number, someone should be able to understand. We all know what that is, okay? But if this is like an airport identifier, we may want to go further in explaining what an airport identifier is. So we'll discuss the length, if it has a default value. So for example, if we're building a database for the Redmond Airport, most likely the airport identifier will be RDM. And nearby airports, BND might be listed, those kind of things, okay? So it depends on what we're doing. Sometimes the default values are filled in based on previous entries into a database. Okay, so if we're talking about a flight, that originates out of Redmond, we might autofill the airport as RDM, for example. Okay, so source, security, responsible users, description and comments. Again, you have clear and concise descriptions. Make sure if you're coming in and you're editing the data dictionary, we want to know, the edit date, the last time it was touched, for example. Most companies now using ISO, International Standard Organization practices, are going to want to know who edited the data. So it was edited in the data dictionary, and then maybe it was edited in the actual database and what days those changes were made. So documenting the data flows, so data flow name and label. So just like we did with our graphical representation, we're going to create a document of that. The description, any alternate names that we give it, the origin, destination, volume, and definitely frequency. So how many times is this data flow or this process going to be affected? About 20 times a day in this case. Okay, I encourage you to pause and go through this. I'm going through it at a higher level for you. So documenting the data stores, same thing. So we're documenting the elements, we're documenting the processes, we're documenting the stores. When we get done, we have all the information that's needed to create that database, to program that database. And a lot of times, if we do this in certain software, it will generate some pseudocode out to be able to successfully create a database. Attributes, so descriptions or adjectives that describe the data store. So what kind of information is stored in the data store? Pricing detail, product detail, inventory changes, those kind of things. So, and again, volume and frequency. And here's the processes. Each process would have a name. Okay, so verify order. We've seen this one before. Notice down here, description, accept or reject customers. So you see much more descript here. Okay, when you're writing data dictionaries, it is like writing code. You can't just write the code. We need to write information into our code called comments that explains what the code does, how it does it, what is it using, where is it drawing data from, what's the process that's going on onto the data. So you get the idea. So documenting the entities, the external entities we talked about, so when we're done, we have all the information on everything that's going to affect our data or allow us to create a database, and sometimes maybe even some temporary flat files. So the records, so the record name, which is the combination, and of course, what's it going to do? It's going to give us each element, customer number, customer status, customer first name, customer last name, etc. And then it's going to reference back to all of those elements. And just like the elements referenced back to, say, what record it's in or what table it's in, etc. So we get the idea of how we can create this. And of course, using software like this certainly helps because we can start creating those links between tables, between data, where to find the data, how often the data is going to be updated, how much memory is going to be used to store the data, how much processing. You get the idea, I'm sure. So data dictionary reports. So we're talking about not reports created from knowing what elements of data are available, but these are actual reports that report on the data dictionary itself. So of course, an alphabetized list of the data elements makes sense. If we're looking for a particular data element or we're trying to figure it out. Again, the name should be descript, so we wouldn't call social security number, the X23V data element. What the heck is that, right? So we want to, element names that are clear and concise. Same thing with programming. When we're programming in a variable, we want that variable name to describe the information that's going to be stored or processed in that variable. So a report describing each data element and indicating the user or the department that is responsible for data entry, updating, deletion. Sometimes we go as far as to say what department is going to be using the data. Okay, so who are we reporting this data out to? A lot of times we're able to compile and consolidate our database by, well, someone says, hey, we need this data element. Well, are we doing any reporting off of it? Are we processing data with it? If we're not, why are we storing it in the database? If we're not going to use the data to create information, don't store the data unless there's another reason why. For example, we might store data that a governing body might want to come in and ascertain. So even though we don't use the data, someone is going to request the data from us. So detailed reports showing elements, do a report by element, by record, by data flow, by process. That all makes sense. Start linking that data together. So process description tools. So typical process description tools include, structured English, decision tables, and decision trees. The if statement, right? If this, then that, else do this. So if it's not true, if we check if an employee has over 40 hours, then process their hours this way, else process it this way. So if it's under, if it's equal to or less than 40, process as regular time, that kind of thing. So process description tools also can be used in object-oriented development. So we see a lot of this today where object-oriented programs create objects, and we're going to talk more about this in a subsequent chapter. But those objects encapsulate all the information we need about the object, like a customer object is going to have attributes. Okay, it's going to have processes or methods, as we call them, and stores rather than separate components. So rather than storing as a separate component, it's all stored as a single object. We can then instantiate that object multiple times within our program to store information, say, for many customers. Okay, so process description tools. Here's a great example. You may have seen, those decision trees, on how workflows work, etc. So here's one: hours, greater than 40. Yes, calculate overtime pay. No, do something else. So there's the example that I just gave you. Okay, and a lot of times we may iterate through this if we're doing nested if statements, or we might say, do this until you reach a certain number, for example. So we would sequence through, end of file. Well, we're doing something, we've hit the end of file, if we haven't hit the end of file, print the paycheck. When we hit the end of file, yes, stop printing paychecks, basically. Simplifying it, but you get the idea. So in structured English, okay, follow the rules. So use only 3 building blocks of a sequence, selection, and iteration. So sequence, selection, or iteration, those are the 3 main building blocks. Use indentation for readability. We do this with programming. So for each order, if customer status equals yes and product detail equals okay, then the output is to accept the order, else reject the order. Okay, now there might be something we do behind the rejection, a subsequent process, for example. So, limit vocabulary, use the standards, if, else, all the good stuff that we find in programming tools. So, on to decision tables. We'll get an example of this in a minute. Shows a logical structure with all possible combinations of conditions and resulting actions. So an example would be I put a credit card into the ATM. It comes up and says enter your PIN. Well, if I enter it correctly, okay, then it goes to the next step. If I enter it incorrectly, it may give me another time to enter it. It may iterate through that process 3 times before it says, okay, if you don't get it right this time, we're just going to keep the card, and then you have to go claim it from your bank. And of course, that's a security issue. If you lose your card, someone tries to use it and guess your PIN. So it is important to consider every possible outcome to ensure that you it should say that you have overlooked anything. Well, you don't want to overlook anything, so you got to go through every possible thing, and your decision table needs to list every possible outcome. So you can see how a decision table, like a project, is going to grow exponentially each time we give it another possible outcome. So there might be an outcome that leads to 2 outcomes. Those outcomes lead to 2 more outcomes depending on what the previous results were. So if it was true here and true here, then we do something, or if it's true here or false, we do something else. So the number of rules doubles, yeah, each time you add a condition. Well, if you think about this, we saw this when we talked about the complexity of a project, adding just 1 more person, right? The number of communication channels exponentially grew. It's the same kind of thing here. So can you have more than 2 possible outcomes? Well, that's possible. If so, how are we going to, deal with those? And we have to deal with those by saying, okay, if it's this, we do this. If it's not, then we might check it again to see if it's this or this. We get into what's called nested if statements. So often the best way to describe complex set of conditions, because again, a decision table is going to give us sort of a representation of all the possible outcomes. Okay, so great examples here. I'll just go through a couple. If we do a status check and it's okay, so we get a yes here or a true, and the product is in stock, true, we accept the order. Okay, if it's true that we have a good credit check, but the product is not in stock, we're going to reject the order. Okay, now keep in mind, accept or reject, we may actually put the order in a back order status. So why did we reject it? Well, product's not in stock. Well, are there any in order? Yes. Or are we planning on reordering? Yes. Well, then it might go to a 3rd state. Okay. So you get the idea. And then, of course, no credit status we reject. And then, of course, no. So if you see, here are the 4 possibilities with 2, inputs that we need to deal with. So you can see how this is going to exponentially grow as we go through. Notice here we've added, another outcome, and you see that the possible outcomes now has doubled. Okay, let me go back real quick. We had 2 inputs, which means we have 2 possible results, and 4, 2 to the 2, okay, and then we come up here and 2 to the 3, giving us the 8. So you get the idea there. More information on process description tools. So here you go. Waiver of credit. So because the product is not in stock, the order conditions do not matter, right? So if it's not in stock, then waiver from the credit. It doesn't matter. It's not in stock, so we can short circuit and say no because it's not in stock. Versus here, because the other conditions are met, the waiver does not matter. So this is the idea that because their credit was okay, we didn't need the waiver. Here, you notice their credit was not okay, so we have a no and a yes, the product is in stock. So in order to process the order, we need a waiver from a credit manager. So these will make sense. Again, I encourage you, pause the video, go through each section, maybe come up with your own idea. I'm not going to require this week with homework, but with your own ideas of how this might work in a situation that you're in. Okay, so go through a little bit more on the process description. Preferred customer, order over 1,000. Used our charge card. Discount plus an additional discount. You get the idea. So more on process description tools. Sales promotion policy. So the final version of this. Preferred customer, order over 1,000. All these things need to be met. Okay, and what happens? And if you notice, if they're not a preferred customer, well, we just shortcut that right to $5 bonus. If they are a preferred customer, was their order over 1,000? Yes. Okay. Did they use our card? Yes. They get the 2 discounts. If they didn't use our card, well, they just get the 1 discount. Order over 1,000? No, they just get a $25 bonus coupon. So get the idea here. This is my favorite type of decision tree, a graphical representation. I like tables, don't get me wrong, but this just to me seems more simplistic, and I've found that end users, especially and business people, can follow this because it's easy. It's a yes at the top and a no at the bottom, and we see the results here. Okay, either can be used programmatically. Okay, so but you can see from a programming standpoint, this gives us a little bit more information as to a path, to create a process that would then mimic the decision tree. So again, go ahead and pause as we go through. So logical versus physical models. While structured analysis tools are used to develop a logical model for the new information system, such tools also can be used to develop physical models of the information system. So again, these tools start developing code, or as you saw in our description, we start putting in code that would process the process. So that's that stuff behind the black box. We're actually starting to get into physical model. Now this is a little tough for some folks to follow, but because, well, it's all in the computer. I don't know what's going behind the scene. Well, I just try to, remember that software is physical, okay? It's logical and physical, yes, but it's physical. It's a product that we're using. So although we can't touch it and feel it, it's been created. And that's the idea where, we take logic from the mind and create something that's usable. Okay, so physical model shows how the system's requirements are implemented. Okay, it again may also be like a prototype, for example, would be the physical model of our logical plan. Okay, so sequence models. So many systems analysts create physical model of the current system and then develop a logical model of the current system before tackling a logical model of the new system. Now, why would they do this? To better understand that system. What this may mean is if we have a data dictionary for the system we're currently using, we can see all the elements of data that we might need to include, what kind of processes are being done if we're going to program one ourselves. Okay. Now, a lot of these steps, like a data dictionary, if you're buying a third-party product, they're most likely not going to give you a clear data dictionary. They'll give you a subset of it, but if they give you that, they're giving you their product essentially. Maybe not all the code, but they're giving you all the information they're storing, how they're storing it. You could take that, build your own database, right? So we be careful when we give that out. If we're buying third-party products, or Quicken's not going to give you their data dictionary, for example. So performing that extra step allows them to understand the current system better. If there's a current system, it certainly does. However, we're going to spend a lot of time. We're going to spend increased cost. And the question is, how much are we trying to mimic the current system? Is it just that we're trying to bring the current system, which works well and the processes work well, into a modern computing environment? If that's the case, or move it from an in-house app to a web-based app, then it may be very worthwhile to go ahead and create a physical and logical model of the old system. So, four model approach in development: physical model of the current system, logical model of the current system. Then you see we build a logical model, all the documentation, right? That's our logic of the new system. And finally, a physical model of the new system. So only disadvantage, of course, yeah, added time and cost. So the question is, are we going to get enough value to go through that whole process? Okay, if we're looking at a system and going, boy, the new system just does not work, it may be beneficial to say, we're not going to look at a system that doesn't work to figure out how to program a new system that does. We're just going to look back at the old system to figure out what doesn't work, maybe what does work, and then literally jump away from it and create our own system. Another reason why we might do this is we don't want to get stuck in doing things the way the old system did them. We might want to be thinking about, okay, how can we do it better? You know, how can we shortcut processes? Do we need to store the data? Those kind of things. So here's the chapter summary. You can go ahead and pause on each sheet here. And that's all we have. So if you have questions, certainly let me know. Have a great day.